Hi everybody, welcome to another video in Calculus 1, section 4.3, mean value theorem. So mean value theorem, this section, it is an extension of the intermediate value theorem that we have in chapter 2. So before we go to mean value theorem, a special case for the mean value theorem is the Rolle's theorem. So the Rolle's theorem said, let the function be continuous on a closed interval and differentiable, meaning derivative exists on an open interval. And this is the special case in the Rolle's theorem. We have f of a equal to f of b. We meaning the values of the endpoints are equal. Yeah, they have the same height. In that case, it says there is at least one point C in A in the interval A and B such that the derivative equal to 0. Right. So it says that if we have 2 points on the same level, by same level I mean they have the same y values, and the function has to be continuous and differentiable. It cannot go continuous and differentiable, so it can be like this. It cannot go like this. At this point, derivative does not exist, so it cannot be like that. It cannot go like this either, because the function has to be continuous. So we cannot have where it's not continuous, and we cannot have where derivative does not exist. Excluding all of those, the function has to be continuous and differentiable from end to end. So in that case, if it is the case, then there will be a point where derivative equal to 0. Of course, there where we have the horizontal tangent line, right? So that's what the Rolle theorem is about. Now, next, the mean value theorem. It says that if the function is continuous on the closed interval and it is differentiable on the interval, so the endpoint for differentiable is not really important. And it says that there is at least one point C, so that equal to that. So what does that mean? So this is a special case when the Rolle's theorem went on the same level. Now, the mean value theorem, that doesn't have to be in the same level. And it shows that if the function is continuous and differentiable, then there will be a point, at least a point, so that on the left hand side here, this is the slope of the secant line. So the slope of the secant line, so here we have a secant line that goes through 2 points. The slope of that line will be the same as the slope of a tangent line at a point. And mean value theorem says that there will be a point. There will be a point where the slope of the tangent line to that point will be parallel to the slope of the secant line. I mean, by the parallel, I mean they are equal, so the line will be parallel. So in this mean value theorem, the left hand side here is the slope of the secant line to the endpoints. And of course the derivative is a slope of the tangent line. So the slope of the tangent line at the point in A and B. So Green theorem, once again, continuous differentiable from n to n. Of course, I said that is not very precise. Continuous on the closed interval, differentiable on open interval. So the endpoint does not matter on the differentiable thing criteria, right? So in that case, the slope of this line, there will be a point in the middle, so that the slope of the tangent line at that point is the same as the slope of the secant line to the 2 points. Since they have the same slope, those 2 lines are parallel. So the Rolle's theorem, when they on the same level, and the mean value theorem, so we can tell that either case, when we have the tangent line parallel to the secant line, the secant line to the 2 points, the tangent line at a point in the middle. Right. Now, first, for the function that, so that there is at least one critical point in the interval of 0 and 5. So what is a critical point? So critical point is where derivative equal to 0 or does not exist, right? We're not going to consider the case does not exist, because in here the function have to be continuous and differentiable. So we're not going to have that where it does not exist. Right. So what do we test? Okay. How about we have the endpoint? So let's just see what happened at the endpoint. Right. So see, we have a function x cubed minus 7x squared plus 10x plus 3, right? Let's find the values at x equal to 0 and x equal to 5. It's 13, and how about 5? Okay, yeah, make sure I enter the function correctly. Right, x equal to 0 should be 3. Trace when x equal to 0, y equal to 3. And x equal to 5, the values is also 3. So meaning that they're on the same level. Right, so we can sketch. Here's 0 and here's 5. Both of them equal to 3. So in this case, if we look at the perspective of the mean value theorem, it doesn't matter if they are at the same level or not. The function doesn't matter how it goes. I'm just going to draw like that, even though it's not. In that case, they have to be a point parallel to this line, right? So the slope of, there will be a point where the slope of the tangent line will be the same as the secant line, the slope of the secant line. The slope of the secant line in this case is equal to 0. So that's why there will be a point in the middle where derivative equal to 0. So this is a special case in where we call this is a Rolle's theorem. Rolle's theorem, where we have the endpoint have the same y values, the same level. So if we have the same level on the endpoint, there must be a critical point in between if it is continuous and differentiable. So the way we show this is, first, f of x is x cubed minus 7x squared plus 10x plus 3 is continuous on the interval 0 to 5, a closed interval 0 to 5. Second, the derivative 3x squared. Then you say, why do we have to take derivative? Well, we see 14x plus 10. So this is a polynomial. Of course, that is also defined everywhere. On the closed interval 0 to 5, meaning that the function is differentiable on 0 to 5. And then finally, we have the values of 0. The values at the endpoint are equal and equal to 3. So we have 3 of those by Rolle's theorem. They exist upon, maybe at least upon C in the interval from 0 to 5, such that derivative equal to 0. Of course, derivative equal to 0 meaning that there is a critical point in between 0 and 5. There's a critical point on 0 and 5. Right, so that is the Rolle's theorem, special case of intermediate value theorem. So we have to check for those 3 things. Right. Next, determine whether the function satisfies the condition for mean value theorem. So this one should be obvious. This indicate that is mean value theorem. So first, the function is equal to 2x cubed minus 3x plus 1. It is a polynomial, therefore it is continuous and defined everywhere. So it is continuous on the closed interval. Yes. Second, how about the derivative? Derivative is 6x squared minus 3, and it is defined everywhere. And certainly defined on the open interval. So in that case, it is differentiable. On negative 2 to 2. And yeah, so that's satisfying. So we can use the mean term. Next, if so, find the point guarantee the theorem exists. So first of all, we have to find the slope of the secant line. So the Green theorem says, the mean value theorem says, the slope of the secant line, there will be a point where the slope of the tangent line will be equal to the slope of the secant line to the endpoint. So first I find the slope of the secant line. which is at the endpoint. So f of 2 minus f of negative 2 over 2 minus negative 2. So I enter the function. Of course, no, that's different function. So let's do that again. 2x cubed that is clear. 2x cubed. I should keep more space here. I'll do that on the note, don't worry. Minus 3x. I'll change the note and add more space here. Minus 3x plus 1. Right. Let's find the values. At 2 is 11, as negative 2 is negative 9. So 11 minus negative 9 over 4. So that is 20 over 4, so it's 5. So the slope of the secant line is 5. Now if the slope of the secant line is 5, we need to show that there will be a point where the derivative is equal to 5. So slope of the secant line, slope of the tangent line of course that's just the derivative, right? 6x squared minus 3 right, and mean value theorem says those are equal. And then we just need to find the point. So it's easy, make them equal. So 6x squared equal to 5 plus 3, so it's 8. Divided by 6 on both sides, so x squared is equal to 8 over 6 or 4 over 3. So for x, taking the square root on both sides, and don't forget there's a plus or minus. Plus or minus 4/3. And so we have square root of 4 divided by 3 is 1.15 or so. So there will be a point, and we found there are 2 points where the slope of those tangent lines go to that point equal to the slope of the secant line go to the end point. So mean value theorem certainly works. So I mentioned before, mean value theorem is for the derivative is just like the intermediate value theorem for the function. The function says if it is continuous from here to here, it will have to cross the line somewhere. If the function is continuous, then they have to cross the straight line. The mean value theorem says that if the function is continuous and differentiable, it's very important that it has to be continuous, otherwise there will be no points that satisfy it. And it has to be differentiable, otherwise it will not satisfy. So continuous on the closed interval, differentiable on an open interval. If this is the case, the slope of the secant line through the endpoint will be equal to, I should say that backward. Let me say that again. The function is continuous on the closed interval, differentiable on an open interval. Then there will be a point where the slope of the tangent line at that point will be equal to the slope of the secant line through the endpoints. So, once again, there will be a point in the middle of the interval, so that the slope of the tangent line at that point will be the same as the slope of the secant line through the endpoints. And of course, when the slopes are equal, they are parallel. So you could say that there will be a tangent line at the point in the middle that is parallel to the secant line to the endpoints. But of course, that's all there is to it about the mean value theorem. And with all of that, it says that if the function is differentiable and the derivative equal to 0 at all the point in the interval, then it is a constant. Right? Yeah. So if we have differentiable and all derivative equal to 0, so pretty much, of course, if we either go up or down, the derivative is not equal to 0 anymore. So in that case, we cannot go either up or down, so it can only go straight. And if it is for the whole interval, then it must be going straight like that, and it must be a constant. And then next, if two functions have the same derivative, then they're only different by a constant. Right. So that's nice and all, but when we go to section 4.9, I think this will be a lot more important. But for now, I'm just going to put that because it is in this section. But we'll get back to this in the section 4.9. Oh, right. So that's all I want to cover in the section 4.3 mean value theorem. So just that theorem, and then of course the row theorem is the special case when there's have the same level, the same y values at the endpoint. So in that case, the secant line we have the slope equal to 0. Yeah, if we have the same endpoint, the same y values at the endpoint, the slope of the secant line is equal to 0, and that's why there will be a point where the slope of the tangent line equal to 0, which is the slope of the secant line in this case. So row theorem is a special case of the mean value theorem, which is just that. Right. So I stop this section here. As always, thank you for watching, and see you in another video in Calculus 1.